So I think let us start. It's already 3:06. So good afternoon. Welcome to the discussion series on natural convection heat transfer and diffusion mass transfer. Let me introduce myself. I am Shabarish. I am the PhD scholar and the Prime Minister's Research Fellow in the Department of Mechanical Engineering at IIT Palakkad. So this session is actually conducted as a part of our PMRF ISSS series. ISSS is a body actually involved in, it's called as the Institute of Smart Structures and Materials. So they are essentially involved in the manufacturing, design, and of the several kinds of silicon structures. They are also interested, it's a professional body interested in conducting a kind of webinars, discussions, etc. So currently, they are facilitating some opportunity for PMRF fellows to have some online sessions. So this is our course plan. I hope that my screen is visible. So at any point of time, if there is any problem, please tell me so that I can check it. So today our area of discussion is natural convection, also called as free convection, and the diffusion mass transfer. Okay. So unlike other sessions which we may have attended, this session is planned to be kind of a problem-solving sessions rather than complete theoretical sessions. So what I plan to do is like discussing the concepts or some ideas of this free convection as well as mass transfer through some discussion of problems and other factors. So initial part is dealing with the free convection part, and the later part is dealing with the diffusion mass transfer part. So sessions are actually planned to be of around 20 hours, and it's planned to be starting today and ending on 21st August. So essentially we will go through many concepts. We will start with introduction session today. So we'll just have a brief discussion of some important sessions or topics, and slowly we will move on to some problem sessions, discussions. So if at any point of time, if you feel some kind of unfamiliarity in problem solving or some part, you can ask me there itself so that I can discuss. And also the concepts will be discussed. If at any point of time some concepts you are not familiar or not clear to you, how that thing comes, suppose a kind of assumption is taken, so how that is done, etc., you can just ask me, no issues. So as you can see here, so a free convection, like simple examples in our daily life includes cooling of a coffee cup, and also an electronic fuel cooling of an electronic chip, then cooling of nuclear reactor rods, etc. And so free convection, as the word says, it is free, or it is also natural convection. It's also called as natural convection. So we'll see what are the other types which you may be familiar, like free and forced convection types. So you will be getting to know how that is applied to several problems. So diffusion mass transfer is the second part. So essentially, why this is discussed is they are somehow they are interconnected, because this topic is not that much taught in maybe in our during our graduation time or something. So it's actually a very important topic. So I thought of combining them. Actually, the analysis of both of them is somewhat similar. So combining those two, which has got real-time aspects, we can discuss those things also. So some examples include deodorant spraying. Suppose if you spray a deodorant, there is a diffusion of mass into the space. Then the evaporation of water in the lakes, which actually adds water into the atmosphere. Also the penetration of water into the soil, etc. These are some of the common examples of this diffusion mass transfer. So let us see that later. So today we will be dealing introduction to free or natural convection. So today our objectives will be to understand what is what. We'll see some examples or some images and why this to study this and how we can approach and what will be coming in the next sessions. So first of all, let us see what is heat and heat transfer. So anybody knows what is the difference between heat and heat transfer? Anyone? Okay, so what is actually heat? So first of all, let us see a video of this melting of ice. So you can see the ice has melted finally into, it's actually not an immediate process, but it's actually happening through a lot of time. So that video is recorded. So it's a transient or the time varying process. So you can see that ice was there, it fell into the water, it absorbed some heat, and it finally changed into the water phase. So what has actually happened here? So this is actually mixing of two states actually. So ice is in a solid state, water is in a liquid state. So melting of ice is actually called as, the process is called as fusion. So there are several kinds of heat involved, as you may know, latent heat, specific heat, etc. So these quantities are actually to quantify the amount of heat. So then what is actually heat? So what is actually heat? So energy can be broadly divided into two types, heat as well as work. So it's heat as well as work. They are essentially two forms of energy. Okay. So heat is usually denoted by Q. Work is actually meaning mechanical work. In our context, or in terms of heat transfer or in heat, the work means the mechanical work. For example, if there is a tank like this and a fluid is filled inside this, you are stirring the fluid like this. Okay, so this is a kind of a shaft work, isn't it? So by doing this shaft work, we are actually increasing the energy of the fluid, right? Energy of the fluid is actually increased. We are giving, supplying some kind of a work which is actually converted to energy. So in this melting of ice, is there a kind of work actually involved? No, because ice is here, so heat is actually rejected. So no work is done on the system. Work which is denoted by W, and Q which is denoted by heat. So only heat change process, or sigma Q, there is a net change of heat only happening. For ice, actually what has happened, it has taken some heat inside. And what has happened to water? It has lost its heat. So Q reduced. So there is a balance of heat. So the amount of total heat involved in this process is actually constant. If there are, so in a system, because according to the law of conservation of energy, energy can neither be created nor be destroyed. It only changes from one form to another. So we should understand actually the difference between heat and heat transfer. So in heat transfer actually occurs, which is actually the transfer of heat, which is actually occurring due to the temperature difference between a body and its surrounding. Suppose we have a body, or if we have that ice here, and the surrounding is at a different temperature, say 30 degrees Celsius, and ice, which is maybe at 0 degrees Celsius. So there is a net heat flow into the body. So Q is actually the heat transfer has actually occurred. So there is a direction for that. Heat is actually a scalar quantity. It tells us how much, but heat transfer is a vector quantity. It has got magnitude as well as direction. So that point you need to understand. Okay, so moving on. We cannot proceed further without mentioning about the basic laws of thermodynamics. So essentially, we can see all energy change process in the universe actually satisfy these three laws of thermodynamics, isn't it? So most of you may be familiar with the zeroth law, first law, and second law. So zeroth law actually deals with the concept of thermal equilibrium, which means that if a body A is in thermal equilibrium with a body C, And if another body, B, is actually in thermal equilibrium with C, which means that A and B should be in thermal equilibrium with each other. So that was the proposed zeroth law of thermodynamics. Then came first law of thermodynamics to actually quantify the amount of heat. Q is equal to U plus W. Q is the heat, U is the internal energy of the system, and W is the work done by the system or on the system. So heat is also can be added or released from a system. If heat is added onto a system, then Q is considered positive. If heat is rejected from a system, Q is considered negative. Similarly, if work is done by a system, then work is taken to be positive. If work is done on a system, that is negative. Suppose I have previously shown one example, rotating that shaft. So we are actually doing the work on the system. So how should the convention to be taken? The system is not giving any work. We are giving the work. So it has to be taken negative. Okay. So such conventions are there. So that is essentially the part of the thermodynamics. Then, as I said before, Q was quantified. Q, U, W was quantified. But there was not surety in the direction in which heat transfer would occur. Then came second law of thermodynamics, which actually tells us what is the direction of heat transfer. Like, suppose there is a cold body here, as I said, maybe ice, and there is a hot body here, and suppose they are kept very near to each other. So, is this direction of heat flow correct? Cold body to hot body? No, it is not correct, because heat cannot travel from low temperature to high temperature without doing any work. So heat always flows from a higher temperature to lower temperature. So in case if we need to do this process, what we need to do? We need to give some external work for this process to happen, which is actually happening inside a refrigerator. We are giving work inside a refrigerator, or if you want to take heat from a substance, we have giving work so that heat from the body is taken away and released it into the surroundings. Okay. So I would like to ask one question, like, is there any difference between thermodynamics and heat transfer? Why should one study this separately? Anyone? Anybody would like to answer this thing? Like, why should we study thermodynamics and heat transfer separately?
Thermodynamics is with the amount of heat transfer.
Okay.
But in heat transfer, we can study the different modes of heat transfer.
In heat transfer, can you make that once again?
We can different modes of heat transfer, like convection, convection.
Okay.
And the temperature distribution within a body.
Okay, that's good. But why couldn't we accommodate that in thermodynamics actually? We could have accommodated maybe modes of heat transfer also in thermodynamics, right? But why didn't we accommodate that in thermodynamics? Okay. So that's actually a good question to think. So thermodynamics essentially deals with the study of the systems actually in equilibrium state. So when we say equilibrium, we say chemical equilibrium, thermal equilibrium, etc. So when a system is in equilibrium with the surroundings, it has to satisfy three kinds of equilibrium: chemical, thermal, and mechanical equilibrium. I think. Okay, I'm sure. So these kinds of equilibrium it has to satisfy. So the thermodynamics actually studies that systems which are in equilibrium. But heat transfer actually studies a system that is not in a stable state. Maybe it is trying to achieve that kind of equilibrium. So heat transfer is somewhere in between, traveling from non-equilibrium state to equilibrium state. In this process only the modes of conduction, convection, etc. happens. So we can't accommodate that equilibrium here. And also, as I said before, there is a direction of heat transfer. So that factors and analysis all should happen in a state of non-equilibrium. So that's what is essentially difference between thermodynamics and heat transfer, and we couldn't accommodate that in thermodynamic study. Suppose we can see I have pasted one image here actually. So this is actually a Pepsi can bottle. So like suppose there is fluid inside this, maybe Pepsi or cola or something. So if specific heat of the that fluid is CV, which is means specific heat at constant volume. CV. If it is at constant pressure, you will denote it as Cp. So mass is m, and it is initially at temperature T1 and finally at a temperature T2. So in the absence of any work interaction, how can we quantify the heat? So we will just use this equation, puzzle of thermodynamics, Q equal to U plus W. So suppose initially it is at a temperature T1, which may be greater than the ambient or less than the ambient. So T2 is the final temperature of the system. So we are not doing any work. The system is actually in a free state, or we are not supplying any external work. So it's actually the differential form is delta Q is equal to delta U plus W. So W goes to 0 because we are not doing any work. So any heat transfer occurring has actually resulted in changing the internal energy of the fluid. So Q is actually equal to delta U, which is mass of the fluid into CV into how much temperature difference that has occurred in the fluid. So internal energy is a function of temperature. Suppose in a room, if the temperature is increasing, then the internal energy is increasing. Inside a room, if the internal energy is decreasing, which means the temperature is also decreasing at a particular pressure. Okay. So moving on. So let us discuss about the different modes of heat transfer: conduction, convection, radiation. Okay. Is there any other form? Anybody has any opinion on that other than this? Because in most of the textbooks, we can see this conduction, convection, and radiation. Are there any other forms of heat transfer? Okay, let us discuss that later. So let us take a simple example of heating a cooker or a plate, like a vessel, plate or vessel. So we are supplying the fuel heat into this. So the three modes of heat transfer would happen: conduction, which will be from the material of the body to the inside. Also, the heat can also travel like from the plate to the handle. And inside the fluid, there will be convection. And after some time, the surface will be heated and surroundings will be at a temperature, maybe T ambient. Or in the further discussion, we can also use T infinity, which is another expression which we can use to denote the ambient condition, T infinity. So there is a surface temperature Ts. So there will be Q radiation. So radiation heat transfer happens through electromagnetic waves. So if it is in the visible spectrum, like if we are using maybe even our body is also a kind of a heat emitting surface. So if we visualize through an IR camera, infrared imaging camera, we can see our own heat, how much heat we are emitting in the IR camera, which actually measures the radiation. It will detect the body temperature based on the radiation from our body. Okay. So conduction, convection, radiation. So what is essentially the difference between this thing? So conduction means, suppose it is happening in this plate area. Okay. So there will be molecules of the substance inside them. So as soon as it receives heat, it will start to vibrate about its mean position. And suppose heat is first received at this point. So this molecule will start to vibrate. And without leaving its position, it will transfer that vibration energy to the next, then to the next, then to the next, then to the next. So similarly, it will reach at this point, say B. So suppose if it is in the case of a handle, this is A and B, the molecules at here starts to vibrate and that energy is conveyed up to this point B. So that's how conduction is happening. So that is inside a material or a solid. That is happens mostly with a solid. So to quantify that, we need to quantify anything. So how is Q conduction quantified? That is actually given by Fourier's law of heat conduction. It states that Q conduction is proportional to thermal conductivity of a body into temperature gradient that is existing. Suppose if this handle's case is taken, if the temperature at here is Ts, the temperature at here is T, maybe Ty, then K into Ts minus Ty by, if delta L is the length or L is the length, then Q conduction is proportional to that. So quantifying exactly, so it is Fourier's law of heat conduction as given. So it is given as Q is equal to minus Ka dt by dx. So this is the Q conduction actually. So area is the area of the heat transfer across the perpendicular area across which the heat is transferred. And dt by dx is the temperature gradient and K is the thermal conductivity of the material. But our interest is in mostly associated with convection, right? So convection is happening mostly with fluid. And how does this convection is happening unlike conduction? Anybody? What is the governing factor in the convection? How is it different from conduction? Is it like vibration of molecules? Okay, so convection is associated with fluids and there the heat transfer is happening essentially because of the variation in the density. How does that variation in density is happening? Because its density becomes a function of temperature. So as you can see here, the fluid has received the heat. So what happens inside the fluid? So the layers which are closer to receiving heat, they will receive the heat and their density decreases. They become lighter. So what they will do? They will rise to the top. At the same time, top layer, there is not much heat flux as compared to bottom. So there the density is more. So that layers would finally come to the bottom. So likewise, a current is set up inside this. That's why this symbol is actually shown. See. So this process repeatedly happens until there is equilibrium. So that's the process happening in convection. So this is happening in fluids where the density variation is much appreciable. So compared to that solid. So in any mode of heat transfer, actually these three would exist: conduction, convection, radiation. But depending upon the situation, depending upon the criteria, we can say that one mode of heat conduction is actually greater than the other. So we can neglect or we can just not take the other factors or other modes of heat transfer that much. So we can concentrate to particular mode of convection. So that is what is essentially with convection. We can discuss that in much detail in the coming parts. So in radiation, what is the difference? So radiation, as I said, it does not require a medium for heat transfer. Okay. So what happens in, there is no need of a medium in heat transfer. So there the radiation is happening through electromagnetic waves. So they do not require a medium for propagation, unlike in conduction and convection. So previously we haven't quantified what is Q convection. So that we will be quantifying as HA into T of the fluid minus T of the surroundings, which you can also write HA T minus TF minus T infinity. But in radiation, this is given by Stefan-Boltzmann law, which states that Q is equal to sigma A T S raised to 4. Suppose if this is the temperature and infinity, minus T infinity raised to 4. Okay. So radiation is the principle by which actually sunlight reaches the earth. So that radiation is heating. Suppose we are standing near to a fire heat surface or something. Suppose somebody is standing. We can feel the heat. Actually, that is mostly happening through radiation. Okay. So understand that these three modes of heat transfer always exist when a heat transfer happens, but one is greater in with respect to another. Okay. So the final question was any other form of heat transfer. Okay, in some of the literature, some of the studies, they consider advection also a mode of heat transfer. Advection means the bulk motion of a fluid is transporting the heat. Suppose a fluid layer is here, and it is at a temperature T1. It is getting transported by a wave of some fluids to another place. So that is actually transport of a temperature to one place to another, which actually increases the temperature at another place. So advection is another form that is considered in some of, at least in some of the literatures and textbooks. Mostly it will be conduction, convection, radiation. But for information, just have a brief understanding of that, just for information. So likewise, I said in boiling of a plate or a vessel, we can see some other applications like in a PCB, printed circuit boards, where there is an internal heat generation happening. So there the heat has to be removed, otherwise it will affect the life of the PCB. So there also we need to make use of these principles. How can we enhance the cooling through these kind of strategies? How can we efficiently design a system such that whether it is convection, conduction, or radiation, which of them should be selected? So that efficiently we can remove all the heat generated and keep it safe. Okay. So this is actually a image like to show what is actually like convection. I have already shown you. So in convection, there are two types, forced and free. Forced means we are supplying energy, maybe some work, so that heat transfer would happen faster. In free convection, we are not supplying any energy. So it is happening by means of the temperature gradient and of the surrounding fluid. Suppose a hot egg, you can see here, it is kept in a surface and air is forced through a means of a fan. It is flowing through that. While in natural convection, we are removing the fan. So to run this fan, we need to supply some electric power. But here we need not give any kind of electric power. What happens is the ambient air will be there. The layers of air which are in contact with the head will be less denser and it will slightly rise high, and that current sets up. Gradually it cools down. So just have a notice of the values of this convection heat transfer. I have said convection heat transfer can be said to be H into area of heat transfer into T minus T infinity. So H is a determining factor. So this is called as the convection heat transfer coefficient. So for free convection, it is 2 to 225 and of gases. In liquids, it goes up to 10 to 1000. Maybe in water case, heat transfer value is high. And in forced convection of gases, so actually it is 25 to 250. You can see at least 10 times greater. Similarly, here you can see forced convection of liquids. It is almost again 5 to 10 times greater. 20,000. So maybe more than 5 to 20 times. So that heat transfer is then another process is in boiling and condensation, where that another factor. So there the heat transfer rate will be very high. It's another regime. So currently we are not interested in that. Our interest will be in this region. Okay. So to have some idea of some of the fluid flow and heat transfer aspects, let me just have a brief discussion on the flow regimes, which will be useful in the further discussion. So whenever a fluid flow happens, suppose a fluid is flowing and a flat plate or some maybe some this kind of flat plate is there. This is a horizontal plate, vertical plate. So as soon as the fluid passes, there will be several regions of fluid flow which is created. First zone will be laminar, then there will be a transition region, then there will be a turbulent region. Okay. So 3 regions are created. So there is a laminar, there is a transitional, there is a turbulent. So laminar is a smooth flow kind of thing. You can take it smooth. And there is a transitional region. Okay. So transition is from laminar to turbulent. Then turbulent is actually a chaotic flow. Chaos, disordered flow. So there are some factors actually characterizing these regions that you may know as in the further discussion, Reynolds numbers, which is actually characterizing these zones. So laminar, transition, and turbulent. So another figure I have pasted here, like this is to understand what is a steady state and unsteady state. So this is a snapshot of a waterfall. So you can see here, this is an unsteady flow. So what is unsteady? Steady state means the parameter at any with respect to time is 0. There is no variation with respect to time. Then that factor may be a function of X, Y, and Z position alone. So in the fluid flow, suppose I am taking maybe 1, 2, 3 particles. In this kind of flow, in an unsteady flow, if I take maybe that X may be a velocity, it can be an acceleration or any other parameter, fluid flow parameter. So if I take U1, U2, U3, suppose at t equal to 0, I take U1, U2, U3. But at t equal to maybe 5 seconds, U1, U2, U3 changes. Maybe U1 dash, U2 dash, U3 dash. It's an irregular further. So it will be actually constant with respect to different position. I mean, it will, but it will change with respect to time. That can also happen. But in a steady state, you see, it's an long exposure of flow, which means that the flow is actually slowly becoming independent of time. So at any point of time you check here, U1, U2, U3 are same at any point of time. So you know that that is a steady state. So there are kind of another assumption like uniform flow. Uniform flow means with respect to position, there is no change. Okay, just to refresh on that topic only, we will discuss that in coming sessions. So governing equations, as just have a brief understanding, we know there are 3 governing equations. There is conservation of mass, momentum, and energy. And we are taking a system. This may be a fluid or any kind of a system. So what happens is, this is our area of interest. So conservation of mass just means whatever mass comes in, it has to go out without any, if there is no accumulation. If no accumulation of mass, mass in should be equal to mass out. Then conservation of momentum, which says that if the body is under acceleration, then the net rate of change of momentum is actually equal to the force acting on the system. Okay, so in a fluid flow concepts, these are explained with the help of Navier-Stokes equation, which takes into consideration, suppose a fluid is flowing, it needs a pressure gradient, maybe dP by dz to flow. Then there will be viscous forces. So that's another factor governing the flow. Then there are convective terms. These factors we will discuss sooner. So when this is a general, Navier-Stokes equations are a generalization of a conservation of momentum equations also. That is mainly used for in our study in our convective heat transfer. So that we will discuss later. So just understand that the momentum, mass, and energy. So according to energy, what is the difference? Whatever energy comes in should be equal to the energy going out of the system. So energy in is equal to energy out. But if there is internal heat generation, what happens? Energy out equal to energy in plus heat generated or internal heat generation. So just have a understanding of that also. Now some important non-dimensional numbers which are used in our study, as you may know, Reynolds number. You can see it's a ratio of inertia force to viscous force on a fluid flow. So rho is the density, V is the velocity, D is the diameter in a pipe flow, and it is equal to L in a flat plate flow. So it is a characteristic length. So you can see some figures here. See laminar flow in pipe, and it changes to turbulent whenever we open a tap. And also in a lighted candle, you can see the candle is lighted, the plume is actually rising. So there is a transition zone, there is a laminar zone, and there is a turbulent or the chaotic zone. So generally, we know that Reynolds number is actually used to characterize this zone. In pipe flow, we know that Reynolds number, critical Reynolds number is used. It's mentioned that it is 2300. So below this, the flow is laminar. And above which it will be turbulent in a pipe flow. In a flat plate flow, we know that it is 5 into 10 raised to 5. Below which it is laminar and above which it is turbulent, generally. Okay. Then some other numbers which are in use is convective heat Nusselt number, which actually takes, it's a ratio of the amount of convective heat transfer to convective heat transfer. So most of the people, when they are explaining, like they will be, they should clearly mention that what is Nusselt number. Nusselt number just means a ratio of their convective to conductive heat transfer. Most of the people say N equal to HL by K, but what does that mean actually? So it is actually a dimensionless number, which actually tells us which of the following heat transfer is more prominent. Suppose in a particular system we are analyzing, maybe in a kind of a fluid flow through a system. So whether it is convection or conduction is mostly happening. So if Nusselt number is very high, what does that mean? Mostly it is convective heat transfer that is happening. So in that system, conduction heat transfer will be less. So in case of solids, we can see that what happens. Solids, the Nusselt number value will be very less. So that we need to understand. Okay. So Nusselt number is a dimensionless number. Advantages of dimensionless numbers, as you may know, like it will be very easy to characterize them, very easy to formulate the relations. So that is actually currently becoming independent of the size or the geometry of the body. So we are formulating, you might have learned the scaling of the factors. So These dimensional numbers helps us in scaling of the geometry. So whether it is a small body or if it is a large body. So just have an understanding of that. This HL by K, which is LC. If it is a pipe or something, it becomes HD by K. Similarly, Prandtl number. Prandtl number, it's not, some people say Prandtl number is equal to mu Cp by K. But what does that mean? It's actually the ratio of momentum diffusivity to thermal diffusivity, which means that in a fluid, what is more prominent? Whether Prandtl number will be much bigger or lesser. So in the case of air, we can see Prandtl number will be in 0.7 nm. So in such cases, like momentum, like diffusivity means the amount of that transfer of something. Momentum carrying transfer. So before thermal diffusivity happens, the moment diffusivity will happen for high Prandtl numbers. So in that cases, Prandtl number will be very high. So what is it important in our study, in our convective heat transfer, is that it is essential in controlling the relative thickness of the momentum and the thermal boundary layer. This concept will coming together. So just understand that this is an important factor in determining the thickness of the thermal boundary layer. So also you can see that it is just a ratio nu by alpha, which is actually independent of any. Here you can see HLC by K, which includes the length or the dimension of the system. But here there is no such a thing. So that is actually only depend upon the fluid and the fluid state. So just have a brief look at this. You can see Prandtl number equal to 1, greater than 1, less than 1 case. So there is a thin thermal boundary layer, there is a thick thermal boundary layer, and you can see how that is actually varying with respect to different Prandtl numbers. So I will just mention that just a relation. It's called as delta H by delta T, which is actually given by the relation Prandtl number raised to 1 by 3. So this is a relation. This is a thermal boundary layer thickness, which will come in the further study. So that's a relation for the Prandtl number. Okay. Then comes Grashof number, which is very important in our natural convection heat transfer, and Rayleigh number. So Grashof number takes into consideration the buoyancy force. So you can see in natural convection, density is varying with respect to temperature. So obviously, when that happens, there are buoyant forces. Like when you dip a fluid into a solid into a fluid, what will happen? There will be weight of the body, then there are buoyant forces acting for the body. So the density variation will be affected in our natural convection. So Grashof number tells us how much that value is significant. So this is given by the expression, just have a look, gravity, thermal expansion coefficient, then delta T, L cube is the vertical height or the length of the body, mu is the kinematic viscosity. So please note that Grashof number is proportional to x cube or length cube times and proportional to delta T. Okay. So another important is Rayleigh number. Rayleigh number is a product of Grashof and Prandtl number, which takes into consideration, like I said, momentum diffusivity to thermal diffusivity, and into Grashof number, buoyancy and viscosity. So it reduces two things. So what is its importance? Rayleigh number is a measure of the driving forces of natural convection. So likewise, what Reynolds number is doing in forced convection, similar effect is happening in Rayleigh number in natural convection. So it describes the behavior of the fluids. So there is a critical value for that. So when the system becomes unstable and natural convection movements take place, this will come into picture. Okay. And the concept of boundary layer, I will just finish it early. So concept of boundary layer tells us that when fluid flows over a plate, the particles which are immediately in contact with comes to rest, while others will continue to move. So what happens? Velocity here is 0, or velocity here is maybe 1 meter per second. Here it will be 3 meter per second, etc. So there is a velocity boundary layer or the velocity gradient created here. Similarly, thermal boundary layer also created. When a fluid flows over a plate, the fluid which is in contact with the surface will attain the temperature of the surface. So there are thermal boundary layer and velocity boundary layer. Okay, so that is called as a slip condition. Suppose a water is flowing over this space and assume this man to be a fluid particle. So what happens? This is called as the free stream velocity, or the denoted as u infinity. So when the velocity of the fluid is happening, so the particles which are immediately here, they will come to rest. But the fluid here comes to, so there is a velocity gradient created inside. Similarly, you can see here when the fluid, like in a river or something where we go, you can see there is the particles which are immediately in contact, they will be at rest. But there is a velocity gradient existing between these layers. Why that is happening? That is because of the viscosity of the fluid. The fluid is viscous. So that is causing actually the velocity gradient to vary. Okay. So this is an image of a velocity boundary layer. So free stream velocity is coming like this. So it touches the surface, maybe a ground or something. So there is a velocity come to 0. Finally, this comes to a free stream velocity. You can see here. So currently you can see there is a gradually it will growth in boundary layer actually happens. So this boundary layer limit is actually quantified as where the velocity reaches approximately 0.99% of u infinity. So wherever in this growth of boundary layer is happening, where the velocity is actually 0.99% of u infinity, that is called as a boundary layer. Outside of which there are only free stream velocity, which is maybe, suppose if you are coming with a 5 meter per second velocity, and here it goes to 0, it may be 1 meter per second, here maybe 2 meter per second. So somewhere here it is maybe 4.99 meter per second or something like that, 0.99% of the u infinity. Outside which is 5 meter per second. So this velocity actually marks the boundary of the boundary layer. So inside this boundary layer, there will be viscous effects. Outside, the viscous effects are negligible. This understanding will be very effective in our further studies. Okay. So similarly, there are thermal boundary layers. So the fluid with the hot stream of velocity is coming, or maybe a cooled air. As it touches the surface, it attains a temperature, and slowly temperature is increasing and going. And you can see the thermal boundary layer thickness. So previously I was mentioning delta H and delta T. So this is the delta H and delta T. This is actually connected with the means of the Prandtl number. So we will see this boundary layer approximations in our further studies. Let's just see, like there are two velocities in V, U velocities created. So in assuming in a boundary layer, because boundary layers are very kind of thin, like although we magnify it, it is very thin to the surface, like it's very close to the surface. So when a flow is happening in a particular direction, and the flow is very strong in this direction, we are neglecting this flow. So that's what is mentioned. U is significant, then V is significant. So X, Y directions are shown. So and the velocity gradient, like dV by dx is 0. Like here the velocity gradient is comparatively negligible with respect to X. And dV by dy is also 0. So with respect to V, components are also neglected. And du by dx, so velocity gradient is only in this direction. Such kind of assumptions are taken. Okay. Similarly, temperature gradient assumptions, that factors and all we will come later. Okay. So let us have some images. How are we visualizing this kind of natural convection? So you can see here some image of Schlieren image. So there are several methods how we can visualize this. Some instruments are there. One is Schlieren interferometer, which can be used to see the kind of natural convection. So you can see the plumes which are rising out of these surfaces. See, it is a Schlieren image of our hand, very own hand, when it is kept in air. This is the thermal image. So you can see the boundary layers here, actually, what I was mentioning, which is actually over the surface. It's very thin, which is close to the surface. See, here it is, there is a thickness variation, you can see. So finally, it is rising to the top. Now, let us see like one video of like how this natural convection happened. So this is a heated plate. So there is a surrounding fluid. Gradually, in that natural convection, you can see the contours are generated, like round kind of contours you can see. Finally, finally that merging of the fully developed state is achieved. Finally, it merges with that contour. And you can see thermal as well as the boundary layer created. So you can see the thermal boundary layer created here. So it's a very like simulation time is very kind of large simulation time. So you should have noticed that natural convection takes a lot of time to happen. So in forced convection, the heat transfer happens very fast, but in natural convection, this happens very slow. But one advantage is that it does not require any power source. It's happening freely. That's why it's called as free convection. So if you are able to explore the potentials of natural convection, we can improve the heat transfer with minimal power consumption. So that was the video of that. So one question is like, does the orientation of the plate affect the pattern of flow and heat transfer? Okay, we'll see that things in the coming session. And whether another question is, if the plate is cooled instead of heating, how does these parameters vary, or like how does the patterns change? How can we understand? Okay. So some other images I have pasted from this textbook, like we can see free convective heat transfer. They are actually visualized this using interferogram, as actually they say. Interferograms, like interference is the principle used to get the image. So this is the figure shown here. So the figure shown here is actually heated plate at a constant temperature. So the pulse heating is given, pulse, which means it will vary with, it will just like a pulse, it will be given heating. So the heating period in a 2-second time, you can see the boundary layer formation here. It's actually wavy kind, it's actually disturbed. Then temperature field also you can see. For a vertical plate. So there is a vertical plate actually. So there is a heat flux discontinuity, which means the heat flux is different in both the cases. Like one top, it will be different, bottom, it will be different. So case A is larger heat flux is located below actually. So more heat flux is here. And in this case, larger heat flux is here. So you can see the boundary layer formation center in that case. Okay. So in the coming sessions, we will be seeing how this velocity is developed inside this natural convection, how we can obtain the velocity. So how this plot is obtained. So this is a plate. It is kept at a temperature Ts, which is actually heated. Ts greater than T infinity, which is a heated plate. So the velocity boundary layer due to natural convection is forming here. So how will we get the velocity? How will we get the temperature? So you can see here, like we will be able to predict this temperature analytically, that relation. It's actually proportional to delta T that you will see. So similarly, in the experiment, they have actually visually obtained that variation. You can see here. So there's a photographed images. So it's very interesting that kind of seeing such images. So finally, I think we can wind up for today with the final problem discussion. So the question is, 1,000-watt iron is left on an iron board with its base exposed to ambient air at 20 degrees Celsius. The convection heat transfer coefficient between the surface and the surrounding is 35 watt per meter square degrees Celsius. Base has an emissivity of 0.6. Surface area is 0.02 meter square. So we need to determine the temperature of the base of the iron. So this is very common in our daily application. You will keep the iron box like this and go. So what will happen to the temperature of the base of the iron, like when it reaches the steady state condition? So this can be actually seen like a vertical plate. The base plate is here. So heat is given 1,000 watts. So what will happen? This will continuously get heated, right? Then the plumes of air which are in contact will be heated. So they will naturally rise, then convection currents happen. So slowly, cooling will happen. That is the case of convection. But what about conduction? What about radiation? So in this problem, to solve this problem, we are not provided with that much data. So how will we assume that conduction is not there? So we will neglect conduction by assuming that the thickness is very negligible. Okay. For the thermal conductivity or the dTq value will be very lesser. But however, radiation exists. Okay, so the surface will be emitting radiation and also Q will be convection. So Q heat is supplied. Okay, so if in a steady state, what assumptions can we make? Let us see that. So we assume that steady operations conditions exist. The thermal properties are at the iron base and convection heat transfer are uniform. And temperature of the surrounding surface is same as of the air. But that assumption is actually, is it correct? Let us assume that to be correct, because in this situation, we know that there is a boundary layer created. So there will be a temperature gradient in this area, but outside only there will be infinity. But we neglect that temperature gradient for this problem. But when we study about that thermal boundary layers and all, we need to consider that also. So how will we solve this problem? So it's just an energy balance. So whatever heat comes in is actually going as Q convection plus Q radiation. So 1,000 watt is supplied, isn't it? So that is equal to HA into T minus TS minus T ambient. Ambient temperature is given to be 20 degrees Celsius. So if we need the, we need actually the Kelvin temperature. So we need to convert it into Kelvin. So 20 degrees Celsius is 273 plus 20, which is 293, plus radiation. Radiation is sigma A into Ts raised to 4 minus T ambient raised to 4. We have converted into Kelvin for this reason. Okay. Because Stefan Boltzmann law states the temperature should be in Kelvin. So sigma is there. Sigma Stefan Boltzmann constant is 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. So let us substitute that values. See, what is the H value here? H value is 35. So how did we get that? Is it forced or free? If you have noticed, I have shown initially some set of values that I have shown for gases. So the surrounding gases, so it will be in the range of maybe 5 to 20 watt per meter. So we can conveniently assume that this is a free convection case. So there is no any fan or something supplying it to cool this thing or something. Okay. So we substitute these values, 1000 equal to H value is 35 into area is 0.02 into TS minus 293 plus 5.67 into emissivity of the body is there. So that is 0.02 into area. No, emissivity is 0.6 actually, sorry, 0.6 into TS raised to 4 minus 293 raised to 4. So currently that has become an expression in TS, which is actually the base plate temperature. So how will we solve that? Either you can assume some values because it's a fourth power equation in TS. Assume some value, substitute by trial and error you can achieve, or you can directly feed it in a calculator and solve it with an iteration value. It will solve it for you. So substituting that, we will be getting TS is equal to 947 Kelvin. So it will be in degrees Celsius, 674 degrees Celsius. Okay, so for curiosity, if we look at what's the melting point of iron? Anybody? What is the melting point of iron? Anybody with a guess? What is the melting point of iron? If you can guess, can put it in the chat box also. Okay, so nobody sure. So melting point of iron is actually around 1500 degrees Celsius. So this surface temperature has reached only 674. So it's okay, it's safe, won't melt. Okay, this for I asked. So see how we approach the problem. So first we need to understand what is a heat transfer rate, how we are going to convert it into the modes of heat transfer. So from heat, we have went into the mode of heat transfer, which mode we have taken. So we taken convection and radiation. Then just verifying the values, like whether it is correct. Then substituting to get TS, then we check whether the results are okay. Otherwise, we need to go and revise this mode or to the mode of heat transfer or through the verify the values. Okay, so this is actually a design question. So there is no problem in the values, but in our cases or when we are designing something, we need to consider all these factors. Otherwise, it may give us some results which may be wrong also. Okay, so these are the reference textbooks which you can refer. This Sengel, Practical Approach to Heat and Mass Transfer. Then comes Incropra. It's a very good textbook in heat transfer. It will be like a good textbook to follow. Then Fluid Mechanics Fundamentals and Applications. Then that also you can do. So in the next class, we will be understanding this mathematically, how we are going to analyze this free conversion. How will we determine this, the boundary layer thickness, what are the governing equations, understanding how that is formed, how it is related to the ambient condition, what is the thermal boundary layer developed. Then some correlations, which will be very useful in determining solving the problems. So which are actually available in heat and mass transfer data book and all. So familiarizing through that, then we will be solving some problems which is related to some PCB cooling. So the component, what are the safe temperatures, then some problems like solving our local house issues, and also we'll be getting a familiarization with that topics. So if that we can clear everything. So thank you for today's session. It's almost 4:10. I took 10 minutes extra. If you have any questions, you can ask. Okay, so I think there are no questions. So if you have any questions, you can always mail to me in the same mail ID. I'll try to respond that fast as possible. And thanks for joining the session, and we can see you next week. Bye.